Good morning, everyone. It's okay to say hello if you like to. Ken Knapp, thanks to the five of you who did that. I'm Ken Knappenberger, the head of the chemistry department in the Eberly College of Science, and it's my pleasure to honor and privilege to welcome you to the second talk of the 2025 Ashtekar Frontier of Science lecture series. This popular public winter series is now in its 31st year. The lecture series was founded by Abhay Ashtekar in 1995, soon after he arrived at Penn State as director of a new research center that subsequently evolved to become the Institute for Gravitation and the Cosmos. It owes its success to the tireless efforts and meticulous planning by Barbara Kennedy, who presided over the series during its first 25 years, making it one of the most successful science outreach events in central Pennsylvania. So this year's lecture series, titled 2025 Year of Quantum, will explore how physics at the smallest scales impacts materials, human health, computing, communications, and more. I hope they shared that with you before you made your talk. The series celebrates 100 years of quantum mechanics and the UNESCO International Year of Quantum Science and Technology, which was designated to recognize a worldwide importance of quantum science and the need for wider awareness of its past and future impact. Okay, so today and for the next 4 Saturdays, you will hear from researchers on topics that explore the depth and breadth of quantum research at Penn State and beyond. Okay, and so all of us have been impacted or at least encountered quantum science in some way. Right, so whether that's seeing the color of a laser pointer or an MRI image through magnetic resonance, right? We've all seen sort of quantum mechanics, quantum science in action. Penn State's especially well positioned to lead quantum research into the future. We have great expertise in chemistry, physics, and material science in the development of quantum materials, the development of quantum algorithms for quantum computation, quantum security, quantum sensing, and a number of people, experimentalists, who can read out and sort of realize those types of sort of processes in practical ways. Let me see. That was my bit on quantum science, and so now I have to go back to the stuff that I'm asked to say. So today's lecture topic, How Chemistry and Physics Come Together in Quantum Materials, is being presented by Lukas Meuchler. You'll recognize him immediately. He'll be the guy talking after me. He's extremely tall and has a lot of hair. So Lukas is an assistant professor of chemistry and physics at Penn State. He obtained his PhD from Princeton University in chemistry. Before moving to Penn State, he was a Flatiron Research Fellow at the Center for Computational Quantum Physics of the Flatiron Institute in New York City. His research primarily addresses interdisciplinary challenges at the intersection of chemistry and physics, focusing on developing new theoretical tools and concepts for guiding materials discovery and design. A focus of his group is to use recent breakthroughs in topological condensed matter physics to analyze chemical reaction dynamics at the properties of quantum materials. And so I would echo that in my own interactions with Lukas, one of the first times that I talked to him, I realized that he really is a physicist, in a sense, who cares about chemical reactions. And it was really cool to see the way that he brings those sort of two fields together. And so hopefully you'll all appreciate that as well from his lecture today. So following the lecture, graduate students Katie Yan and Christopher Daggett will lead a moderated question and answer session with Lukas. So you should have received a pen and paper when you arrived. It's not because there's a quiz. It's for you to write down your questions during the talk, and then our student volunteers will collect them for the Q&A session. So now please join me in welcoming Lukas Meuchler.
Yeah, thank you very much. I'm very, very happy to be here. Let me see if that works. Cool. So I'm very honored to give a talk here. As Ken so nicely said, I'm really in between chemistry and physics. Some people would say I'm a chemist doing physics, some people say I'm a physics doing chemistry. I don't know what I am, but I'm somewhere in between. And so I wanted to use this opportunity to talk a little bit about some maybe opportunities and some very interesting developments in the recent years that really showcase how research at the interface of two disciplines really can push us forward, and why that is interesting. I think that's a general theme in science these days, that we're coming together. We're not deep into a field anymore. We're now exploring the outskirts and what it means to other fields. And I think this is a very exciting development. Right, so maybe before I go into the science, I just want to briefly introduce myself. Ken mentioned that I'm from Germany, so I'm born around here. So this is Mainz. Maybe some of you know Wiesbaden or Frankfurt. Wiesbaden has a big army base. Frankfurt has a big airport. And, you know, Mainz is a small city for, you know, compared to many US cities, but it's a very nice one. So maybe some of you know Johannes Gutenberg. He's the guy who, you know, invented the book printing press. So that's kind of what my city is famous for. We have a very, very nice cathedral that was built around 1000 BC. We have a very, very nice old city. So it's a very lovely little city. We love our wine. We love our food with wine and so on. So it's a very, like, you know, open community. The heart of the city is really the river. So if some of you maybe know Wiesbaden, Mainz, they have a, you know, every city has like a local competition. And so what we say is the only good thing about Wiesbaden is that you can see Mainz from there, right? Because you can see over the river and see the other city, right? So, okay, but actually when I started as an undergraduate at the University of Mainz, I started as a chemist, but I got very, very interested in more physical phenomena. And so I had the fortune of meeting a professor who basically enabled me to go abroad and spend half a year in the US. And that really catalyzed my interest in, you know, pursuing a PhD in the US. I really liked the research atmosphere. And so I started down here in Princeton, where I did my PhD, then moved to New York, and then back here to State College. So these are all three very, very different places. But what they all have in common is that they're extremely interdisciplinary. So, you know, in Princeton, I was in the Department of Chemistry, but the Department of Physics was actually next door. And so I was constantly going back and forth and working with people there. It has really defined my research. And also here in New York, so this institute, this is an institute by the Simons Foundation. It's a private foundation. But the idea is just to bring together interesting and very motivated individuals, and that kind of just throw them together, give them resources, and do work together, right? So I like this kind of research. That's what I thrive in. And that's one of the reasons I came back here to Penn State. Right, so now I have my own group here. I'm very fortunate that, you know, some students have you know, made the choice to actually work with me. I'm very, very happy with them. Our lab has grown and grown over the time. To show you what we do, I'm a theorist, so here are some absolutely not staged pictures of how our daily life looks like. We just think and point at, you know, at data on screens and so on, which is maybe, you know, to 60% correct. But essentially, that's what we're interested in. You know, we don't work in the lab, but what we do is we're trying to develop ideas and computational methods that can help, you know, to understand experiments or even lead and propose new experiments in this field. And so this is the year of quantum mechanics. I'll talk a little bit more about quantum mechanics. But if there's one thing that I want you to take home today, and this is really my main message, quantum mechanics is not mysterious, and quantum mechanics is complicated, but we understand it very well, okay? So you see a lot of quotes around here, you know, if you think you understand quantum mechanics, you don't understand quantum mechanics. These come from the early days of quantum mechanics, but I think this is not true. We as a society, and we especially as scientists, we understand the quantum mechanical rules, the equation, and the outcomes of these equations extremely well. We have reached an extraordinary sophistication in designing new materials, controlling the properties of materials, and that's what I'm going to walk you through, right? You know, there's other quotes like common sense has no place for quantum mechanics, but I think these kind of quotes have no place in science, right? So I think this is more if you want to sell books. But I think what these quotes go back to is that in the early beginnings of quantum mechanics, it was indeed a little bit weird that some of the microscopic behavior is very, very different from how we understand the behavior at the macro scale, right? Like we are on the order of meters, atoms are of the order of 10 to the minus 9 meters, right? So it's a billion times the difference. And so people were very confused because they thought the deterministic nature, you know, of these equations that should go into, of course, what happens in the atoms. But that's not true, and I'll give you some examples how we can actually show that's not true and how that's very important that it's not true. I would argue that modern technology would not be possible if quantum mechanics were to behave as classical mechanics. Okay. All right. So where does this tension come from, right? So essentially, we live in a continuous world, right? Everybody who has burned their hand and on something knows if it's red hot, it's probably very hot, right? And this is basically burned into it, so literally, is that if we look at something that's very, very warm, we perceive the temperature as a function of color, or color as a function of temperature, right? So like if something is red hot, then if you heat it even more, it will become white, and then it will get to like a bluish color, right? What this means is if you heat it a little bit more, it will change the color a little bit. It's a continuous scale, essentially, right? So now, when we look at very, very macroscopic objects, for example, the sun, we can measure what their spectrum is. So what I'm plotting here is a spectrum of the sun in the visible range. This is taken from the Griffith Observatory website. And you can kind of see that the sun emits light in basically every color, if you squint your eyes a little bit, right? But if you zoom in very closely, you see that there are these like black gaps in between, right? So there seem to be some frequencies that are not covered in the spectrum of the sun. And you can actually understand that the reason why there are these black gaps is due to the quantum mechanical behavior of small elementary particles that live close to the sun or on the sun, because they absorb, right? And so problems like this, in the 1800s, people developed theories to describe, how does the color of a material change as I heat it very much. All of these, what you basically get out of these theories is that the color should change continuously. There should not be any gaps, right? But then, once atoms were discovered, people had these skills to actually isolate, certain elements on their own. People started experimenting with single atoms or single sets of atoms, right? So for example, if you take a so-called discharge tube where you basically have hydrogen gas in there and you just apply a very, very high voltage, what you see is that light is being emitted, right? So like many light tubes still work kind of in the same way, a little bit. But what you see here, that the spectrum that is emitted, so what I'm showing you here basically are that if you take this light that comes out of this tube and you put it through a prism, you would see that you don't get a continuum of frequencies, right, of different colors. What you will get is basically you get these discrete lines, right? And there's large black bars here, which means that hydrogen does not emit light at these frequencies, right? And so for the physicists in the early 1920s or early 1900s, this was a huge problem, right? Because they were so convinced that nature needs to be continuous. So why can the emission from an atom, from a gas of atom, be non-continuous, right? So that's one of the first hallmark of quantum mechanics. There's something that is quantized. Quantized just meaning it can only take on certain values. It is not continuous. And of course, people not only looked at hydrogen, they looked at more complex atoms, right, and gases of atoms. So, helium, neon, going through the whole periodic table. And you can see that basically every element we know does emit light once we heat it up, but it only emits lights at very certain frequencies. A very important fact is that these frequencies do not change depending where we are. So we use these kind of spectral lines now to identify which elements are present in galactic clusters, because we can measure the light from there and say, oh, this is this line, and this is this line, and this is this line, right? So, so now what happened, right? So there was a big crisis in theoretical physics. How do we describe this? And so it took two people about 100 years ago. So the first one is Werner Heisenberg. This was a time where you could take off a few months and go to the German North Sea and just say, I'm going to solve this problem now. So what he did is, he had some health problems, and he said, well, I'm just going to have to leave and actually figure this out, right? So he went to, I think, some island in the Northern Sea in Germany and spent a few months there. And then he developed his so-called matrix mechanics, a new version of mechanics, as he called them, that takes into account quantum mechanical effects. And so he was able to develop equations that could successfully describe this quantization of the emissions of these different atoms. As I said, this was a huge mystery. There were some phenomenological models that worked for hydrogen, but in general, it was very, very hard to even understand where they come from. So what one needed was really a new framework, a new set of equations that would allow us to describe these observations. I'm simplifying here a lot. There's going to be a lot of other observations, a lot of other experiments that were very important, but this is kind of my view as a theorist, of course, because these guys developed the underlying equations that I now use in my daily life, right? A year later, Erwin Schrödinger, and this is 1926, this is 1925, that's why it's 100 years ago. Erwin Schrödinger developed a different theory of quantum mechanics that gave the same results, but had a completely different philosophical approach, okay? So he treated quantum mechanics as a wave equation. I'm sure you've heard a lot about this already, that there's this duality between particles and waves. And so it took actually quite a few years until people could reconcile that these two theories actually describe the same thing, right? So it took really the community a long time to understand how they are connected. And even in today's research, we kind of go between these 2 points of views depending on what we want to do. Some are more amenable to being described on the computer, some are better to be done analytically. But the impact of this work was really that it formalized how can we think about quantum mechanics? How do we think about these spectra of atoms? How can we describe atomic behavior, right? And what these theories all predicted is that the energies in atoms are quantized. That means, normally when you think that something is moving, well, it has a kinetic energy, so the energy can take on any value. It turns out that these states in atoms, the electronic states in atoms, they can only occur at certain values of the energies. In between, there's no possible energy levels. This is what we call, a quantization of energy. This caused a lot of problems for people because they were not used to this, right? Famously, Einstein did not believe in any of these things. But what this allowed us to do is to understand, well, how do atoms emit and absorb light? Well, we have an electron at a certain energy level that absorbs light, then it goes up to a higher energy level. Because it can only go from the ground state to this excited state, from this ground state to this. There's only a finite many amounts of how much energy can I absorb, and hence we see this very sharp lines in absorption and emission spectra. Okay? So this was really one of the first times. They provided us with formulas where basically we could then figure out how we could predict these line shapes. And so now, 100 years later, I would argue we have come very, very far. I mentioned this in the beginning. There was a lot of confusion about what the laws of nature should be, how they behave, but we've had a lot of time to figure them out. And so now I would argue is that we're really understanding the macroscopics of atoms, of molecules, of crystalline materials to a really, really high degree with an extraordinary level of sophistication. So this is one of my favorite movies that has ever been made. It's called The Little Boy and His Atom. So what this is, people used the surface of a metal and they deposited carbon monoxide molecules, so CO molecules. So every little thing you see here, this is a CO molecule. This is an individual molecule, and you can see the atoms in there. So within 100 years, we have come from wondering about the philosophy and what these equations mean to actually being able to make devices that we can now control the position and the properties of individual atoms, right? This is insane. I just want to say this, right? We've come a really, really long way. This cannot be understated how important that is, right? I think if you would show something like this to Einstein, Bohr, Pauli, Heisenberg, they would have lost it, right? It's incredible. So I just want to say that I think saying that things are mysterious doesn't really do it any justice because we do understand it very well, right? And I think it takes away opportunities and it takes away, I think, and it's a different approach if we say, yes, we do understand, we can do so many cool things with this, right? So let me try to replay this once again. Does this work? Right, so this was a team at IBM that basically, they have a little tip which they can move the atoms, so they frame by frame, they move these atoms and then took a picture of these things. Isn't that cool? Well, this is just a gimmick, but you can imagine we can use this for storage of information. We're not going to write a novel with individual atoms on the surface, right? That's probably not a good idea. But if we can manipulate and address individual atoms, right, we could probably store information on the atomic size, scale, right? And so this is really something I think I would argue that these breakthroughs in basic research about 100 years, 80 years ago, they have led to the technological revolution that we're now experiencing. So what I'm plotting here is basically the capacity of hard drives over time. This is taken from Wikipedia. And I want to highlight that this is a logarithmic scale. So we start with, megabytes, and we end up with terabytes, right? So I was born in 1988. So, maybe around this time, I was allowed close to a computer without destroying it. And remember, I wanted to install a game, and our hard drive only had 100 megabytes, and the game was like 50 megabytes. My father was like, I do have to work on this. So, I unfortunately cannot let you install this game. Nowadays, 50 megabytes, we don't even care about this anymore, right? So we're now in the terabyte scale, and we can buy these hard drives for, pennies essentially, right? So the amount of breakthroughs we've had over, this is like give or take 40 years, right? These have all been possible because we try to understand the fundamental nature of quantum mechanics, okay? Without these papers 100 years ago, without people trying to understand why do atoms not behave the way we think they behave, this would not be possible. There's another famous example that people often highlight. This is basically what this shows here. This is from an article in Nature. Maybe this is easier to read here. What this shows is basically the number of transistors on a chip, right? So when we have any CPU on a computer, anything in our phone, usually the more transistors we have, the more operations we can do and the faster we go, right? And so this is also on a log scale, right? So this is a straight line, so this is basically going exponentially, right? So we started in the 70s, which is maybe 20, 30 transistors, and now we're in the millions and even billions to some extent, right? This is all only possible if we understand the microscale, if we understand the behavior of atoms, if we understand how to make materials, how to synthesize them, how to control them, right? But we can see this as an absolute success of science, right? This is going up and up and up again. This is something related to what's called Moore's law, where we say basically somebody predicted the number of chips double every so many years, and for now 20 years, every year somebody has said, okay, now we have to stop, right? It's just like not physically possible, but it just keeps on going. But what doesn't keep on going is the speed of the chips, okay? So initially it was also exponential, but now it's kind of flatlining, right? So while we're making things smaller, smaller, and smaller, there is some sort of natural limit, okay, with the current technologies that we're having. Okay, and so now what I want to talk a little bit about, that was in the topic of my talk, is this field of quantum materials. And the reason why I want to talk about is that this has emerged in recent years, and people are very, very convinced that this new look or these new understandings we're gaining in this field about the properties of materials and their quantum mechanical properties will probably enable us to generate even more breakthroughs, even better computers. So I showed you that the speed of devices is kind of flatlining right now, right? This is because we're reaching the atomic limit. We have now transistors that are just a few atoms thick, right? If you've reached one layer of atoms, well, you cannot go smaller than this, right? You're kind of done, right? So there's a natural limit we can reach. There are issues with heat dissipation, right? You've all seen that your laptop gets very hot or your phone gets very hot when it does certain computations. And also with scaling, right? Manufacturing processes become more and more complicated. It is more and more costly to develop faster chips. And for a while now, there have been a lot of proposals out how new types of devices that don't make use of traditional transistors, for example, could potentially revolutionize the field of computing, of magnetic phenomena, of storage, and 1,000 other fields, right? But what I would argue is that we are not that far yet, right? There's a lot of very important and interesting proposals, right? You've all heard about quantum computing and many more, but many of these devices or these proposals, they're really, as we develop the theory, we also have to develop these devices, right? And it becomes more and more clear that this is a very hard thing to do, right? So many of these innovations are really contingent on us finding new materials and new devices right, that could enable these breakthroughs. We know that in principle the laws of quantum mechanics should allow for these properties, but it's very, very hard to actually find, materials that do that. And so I'm between chemistry and physics, so there's two things that are very, very important for me, right? So the first important thing is, of course, that one can conceive of a new idea, a new property, right? And you can show that the laws of quantum mechanics are compatible with these new ideas. So usually what people do is they find a simple model, right? They conjure up some equations that say, look, these equations show this behavior that I want, right? So for example, if my system behaves like this, I could do quantum computing at a high temperature on this. The other thing, though, is that now that we have this idea, and I would argue this is an even bigger obstacle, is we have to show that we can make materials that have these properties, right? That we can actually control this. And so this is really something where I argue we need an integrated understanding between the chemistry and physics. And this is the challenge that is ahead of us, right? I want to explain a little bit more what quantum materials are. I'm not going to go into many details. I'm not going to explain to you. But it basically, some critics say it's a little bit of a buzzword. The way I think about it is the following. All these breakthroughs that I've shown you before, hard drives, chips in the 70s, 80s, 90s, of course they're also all based on quantum, the quantum properties of materials. But I think what has become clear now is that we can develop new devices, new ideas, through the combination of many quantum mechanical effects. And I will talk about one of them today later. Right? What this means is that we're interested in the collective behavior of electrons. Right? So what is the best analogy to this? Just as if we look at a flock of birds in a swarm, right, you can see that there is very orchestrated movement that, they merge, they go away from each other. If you would like to describe this here, you better not describe just what a single bird is doing, right? You want to describe how all of these birds talk to each other, how they communicate, and how you could direct these things. Basically, that's exactly what we want to do with the electrons in these materials. We want to understand how we can steer them collectively, how we can interfere them, how we can make them interact so that they show new properties that are desirable. Okay? So I want to give you one example. This is a field I've worked on for some time. And for that, we need to understand one more thing about quantum mechanics. And that is the spin. Okay? So shortly after people discovered the early equations of quantum mechanics, people have been doing experiments for a long time. Anyways, there were two physicists actually close to where I used to live in Frankfurt, Stern and Gerlach. They had the idea is if we take basically we can generate a beam of silver atoms and we can basically let these atoms pass through a very strong magnetic field. What they wanted to do is they wanted to understand how do atoms interact with strong magnetic fields, right? Because only now had people have the opportunity and the technology to actually generate and control the directed motion of atoms. And so what they did is they were expecting, this silver is a non-magnetic material. We all have silver everywhere. It's not magnetic, right? And so they were basically expecting that these silver atoms should just pass through this magnetic field in a straight line. So this is this dotted line over here. So maybe this is easier to see. But what they saw is that basically half of the silver atoms, they have a detector plate here, half of the silver atoms basically accumulated on the top of this place, and half of the silver atoms accumulated at the bottom of this plate. This was also completely mysterious because by everything people knew at this time, this should not happen, right? Silver is not magnetic. If it's not magnetic, it should not interact with a magnetic field. Normally, when you have a magnet, right, it wants to follow the magnetic field lines. And so it kind of did, but this distribution here was also not very continuous. It was basically either it goes here or either it goes here. Right? And so what this led to was basically the physicist Wolfgang Pauli, who was at the time at the ETH Zurich, he proposed there's a new property of electrons that we don't know about. And he called it the spin. So this picture, what I'm showing you here, is completely wrong, but it's a good analogy. Okay? So what you can think of is that electrons or atoms, basically it's well known when something spins that has an electronic charge, it should generate a magnetic field. So what he thought is maybe these electrons just spin very fast, or these atoms spin very fast. So some of them spin in this direction, so they generate a tiny magnetic field up. That means if you shoot them through this magnetic field, they go down. And the other ones, they just kind of spin in the opposite direction, so they generate a tiny magnetic field that goes down, and then they will go into this direction. Okay. It turns out that this intuition was completely correct, but this picture of spinning atoms or spinning electrons is not correct. But we have now learned that we need to incorporate this property, the spin of electrons, into our equations. Otherwise, everything will go wrong, right? It turns out that this property, the spin, basically the electron can behave as a tiny magnet, is responsible for magnetism as we see it, and many, many other properties. So where is this property of the spin useful? Well, normally when we have devices, normal transistors, right, we just drive a current through a metal. In this metal, we have equal amounts of this left spinning and right spinning electrons. So there should not be a difference. There's basically no selection between these things. What we are probing when we have a device, right, we measure the current, we just probe how many electrons go from here to here, right? That's basically a current. So now over the years, there have been a lot of proposals, and this has become an extremely large field now, where the question is, can we design new electronics and new storage methods, new electronics, by using not only the properties that electrons are charged, right? We apply a current, they go from left to right, but can we make use that they have this property of the spin, which is basically a tiny magnetic field? So it's really a big dream if we could have currents that only consist of electrons with one type of spin, because then this is basically the same as having a flow of electron that has a tiny magnetic field going with it. There's a lot of proposals. There's a whole field called spintronics that if we could do these things, we could build new magnetic storage devices, we could make new transistors, and we could speed out our computations. These materials also do not have these limitations as current materials. And so in around 2005, 2006, there was this very intricate and interesting proposal from some theorists. So this was from Chusheng Zhang and Xiaolong Qi in Stanford. What they said is, okay, you take a material, this material is called mercury telluride, and you make a sandwich out of this. So this dark one here, this is mercury telluride, and this other material that's called the material is cadmium telluride. People could do this since the 80s. People have used these as photon detectors, so the technology to make these things were there. What they said is basically, these materials are semiconducting. What that means at low temperatures, current cannot flow through these materials. This is another quantum mechanical result, but you all know about them, semiconductors. Anyways, so what they were saying is, instead of having electrons being transported through the bulk of the material, the inside of the sandwich here, what if we could have some sort of channel, some highway on the right side of the material and on the left side of the material, and can we engineer it so that the electrons who have this spin up go in the left direction, and the electrons on the spin right go into the right direction. This phenomena is called the quantum spin Hall effect, and the analogy that people at the time always made is, normally when we use any devices to carry electronic current, it's a little bit chaotic, right? So a metal is never really pure, so we have a current going through a material, but there's impurities, there's edges, so things that are scattering, right? There's a little bit of chaos. This, of course, leads to resistance, or the transmission of electrons is not very effective, and that leads to heating, which is one major problem. So what if we could engineer some sort of highway where one sort of electrons is going in this direction, the other sort is going in this, and they don't really talk to each other? That's kind of this idea of a topological insulator. Okay? And so actually in 2007, together with a group of Lawrence Mollenkamp in Würzburg in Germany, they could measure this phenomena, and they could basically show as a proof of principle, this is one of these things I talked about. Some people comes up with an idea, and they work together with other people in the experiment. Can we realize? And they could show that it's indeed true that we can create a device in which no electronic current flows in the inside, but on the edges, we have these states in which electrons with a spin up go to the left, and an electron with a spin down go to the right. This is extremely interesting because now you can basically have spin currents, so currents that consist only of a certain type of spin, and you could use this to then, memory storage and so on, as I mentioned before. So this was a huge breakthrough, an extremely huge breakthrough. It started with a spherical cow in the vacuum where people had some very simple models, And they somehow managed to find a material that could realize it. So, this was great, but then if you talk to somebody in the industry, would you like to make a material that's made of mercury and cadmium and tellurium? Probably most people would say, no thank you, right? Mercury and cadmium, extremely toxic. Tellurium, very expensive, right? And so now what this resulted in is that people understood there's a huge opportunity. People didn't believe this is actually possible, but people now that these experiments were there, said, this opens up a completely new opportunity, a completely new way of thinking on how we could potentially design new materials that have these intrinsic and desired properties, right? But of course, you want something that is non-toxic, something that's made not only from rare materials, but like from common materials. You want to have some sort of degree of tunability, right? We want to be able to manufacture and synthesize these materials in an easy way. And maybe if we can branch out, we can even discover more interesting phenomena beyond these that were discovered in these materials. And so I was very lucky at the time that I was actually visiting the lab of Shusheng Zhang in 2010, so when this started. And so since my training is that basically of a chemist, we immediately started working and trying to understand how can we translate these concepts that these theoretical physicists have come up with into a language of chemistry. Of course, many other people also did the same, because people were saying, hey, if this works on this material, I'm 100% sure it will work in this material. And so what this leads to is that this was not only a scientific challenge, but also a cultural challenge. And that to me is something that's very near and dear to me, because basically we have two approaches to this. I mentioned before that many times, especially in theoretical physics, people focus on the equations, they focus on what we call models, right? Like, is there in principle a system as simple or complicated I want it to be that gives me the desired properties? So this is a picture I stole from my old advisor, Claudia Felser. She had this made by a graphic designer. If you talk to many solid-state chemists and materials people, they think very, very differently. They don't think in these mathematical quantities. They think more about, oh, what happens if I replace manganese with iron? Or can I put zinc in here instead of copper? Let's see, let's try, okay? And so there is a huge challenge to basically find a way to combine these two languages, this very mathematical one, with the more chemical one. And so, long story short, what we have done in the last few years is really shown that we can overcome this gap and that we can find a common language and we can find really, really interesting new materials. So this here is a new material that's very similar to the one that I just showed you, this mercury telluride, where basically in the bulk of the material it doesn't conduct any electricity, but on the edges it does. So this is a paper from a group from Berkeley, Washington. And so what they're doing is there's a material called tungsten ditelluride, which is just 3 layers of atoms thick. And we can produce these materials with extremely high accuracy. So what they're showing here, this in C, this is basically the material that they exfoliated. This is 3 atoms layer thick. And then around here, they have some substrate and some electrodes and so on to measure this. And what they did is basically, they did an experiment where they can image which part of this material conducts electricity and which one does not. And you can see here in these zoom ins, so for example in this area, that the inside of the material does not conduct any electricity. But the edges of the material are extremely conductive. And this is consistent with this picture, basically that at the edges of a material, you have these special states going around. There were later experiments that confirmed that basically these states have a specific either spin up or spin down. This measurement, what they did, is it's not possible to measure this. But the interesting thing is that people discovered is, I just told you that normally when we have something that is metallic, right, that conducts electricity, electrons move, they're usually scattered by impurities, by, if the material has a crack and so on. What they found in these materials really blew everybody's mind. Namely, you can kind of see this material here has some zigzag edges, or if you look over here, there's some cracks in the side. Well, these states at the side of this material, they just don't care. They just go along them. They don't get scattered, they just follow these cracks. And so they made even some more careful measurements, for example, where they take this material, tungsten telluride, and it's kind of folded up on itself, it has some cracks inside. And what they found, whenever there is a defect or a dislocation or anything happening in this materials, the electrons on the edges of this material will just follow this, right? So you can imagine what big of a breakthrough this was, because now we could potentially make very, very, very thin materials. This is just 3 electrons thick, where we have electrons that essentially do not care if there's a small crack, some small imperfection, okay? And so people are very, very excited about these types of materials because potentially we could generate new devices. But again, this is a proof of principle. This is probably, they make 50, 60, 100 devices and they show you 2 out of them, right? There's still a lot of work to be done, but these are extremely important observations that we can build this bridge between high-level theory and high-level experiments. And so I was very lucky that over the past few years, I was part of this field where we discovered not only these materials I just talked about, to you, this like mercury telluride, this over here, but now we have discovered a zoo of new materials that have similarly interesting properties. I'm not going to go into the details here, but of course I want to tell you what that actually means if you do it as a scientist, okay? So in order to explore, you need to have the expertise to synthesize and control the atomic composition of these materials. That requires expertise in chemistry, right? Because that's what chemists do, they make materials. So people have mastered now different types of synthesis methods for different materials. We can make what we call single crystals, where basically these are crystals that are grown in one perfect orientation. Some of them go to these, there's a lot of shows here, crystalline shows, that normally these things need to be grown over hundreds and thousands of years. We can now grow these things very accurately in the lab. But this took quite a while for people to perfect these kind of materials, to perfect these methods to synthesize them. But now that chemists really joined in, this is not usually the expertise of solid state physicists. Now that chemists can basically synthesize a zoo of new materials, we can test all of these materials for their properties, right? Another thing, and that's where my group, for example, comes in, the level of theoretical sophistication is also extremely high these days, right? So I can now, with my groups, we can make calculations and we can predict the behavior of the electrons in these materials rather accurately. It doesn't work all of the time, of course, but in some cases it works very well. So this is one example here, where basically what we're doing here, we're taking snapshots of the electrons at different energies. This is actually a quite complicated experiment, but for us to calculate it, we can calculate this on a small laptop, for example, these days. And so what we can do is we can basically say, where do we expect electrons to be at which energy, and we can kind of resolve this spatially. And so you can see that what we measure in experiment looks very much like that, what we measure in theory, right? This is very nice because now we can screen and explore materials not only in experiment, but we can maybe narrow down the amount of materials that we need to look at from like 1,000 to maybe 20 or 30, right? Which is much more doable. Also, there's now, big data is a thing these days. So now there are people thinking about, well, we have databases of all known compounds we know. Why should we make new compounds when we could just look at the old compounds, right? And so, there's one thing that if you do, high throughput calculations, what basically people have been doing, they've been going through all the databases, basically, they rented supercomputers for half a year and basically just ran calculation nonstop. And then they've developed tools to analyze the outcomes of these calculations. And so, for example, this group here, it claims that about 50% of all known materials have some of these interesting properties that we're interested in. For example, that the spin of an electron depends on the direction it moves, right? There, of course, is a caveat, because if you calculate an insane amount of materials, you cannot do it with the most accurate calculations, right? So I would take this number of 50% with a grain of salt. It could be off by 20% even. But I think what is important to me is that we've really come together. So these guys have made a website where you can basically just enter a compound and they tell you what the properties are from their point of view, okay? So again, nothing will be a proof until you actually make this compound and synthesize it, put it in a device and actually measure it. But these kind of things now allow people that, very often it happens that you're in a university and you want to do something, but you don't have a local expert in these kind of things, right? Back then it would take a lot of time, you have to talk to somebody, you have to communicate, can you do these calculations for me? Now everybody can just go to this website and have this website do the calculations for them, right? I think this is insane, this is really cool. Of course you need some basic expertise and a little bit careful with the results, but I think we're coming to a point where we also pool out this data in a way that's much more available to a large amount of people. Okay. Then, of course, when I was looking for a faculty position, I was extremely happy that I got to Penn State. Actually, Penn State is one of the leaders in this field here. We have an enormous amount of theorists and experimentalists. And more importantly, we have big centers that focus on understanding, characterizing, and describing the properties of these materials here. This is all over physics, chemistry, and material science, right? We have, because we have so much funding from these places, they were able to buy very expensive machinery, and basically they are now able to have user facilities where people from other areas can come in and do the experiments they want to do without having to buy their own machines, right? So I think this is another thing, is that because we're so interdisciplinary, this naturally widens the horizon and basically leads to the inclusion of much more people. And I think the more people think about a problem, the easier it is to solve, right? And so Penn State is really one of the best ones here. Okay. So I'm kind of towards the end here. I've talked to you a lot about science. I apologize for not going into more details. I would rather, for me, it was more important to tell you that really we are so good at doing quantum, okay? Don't believe anybody else. Even if we're good at something, it can still be complicated, right? There's a lot of challenges ahead, but it's fun, it's interesting, we want to do this. It's not mysterious. I don't want to do something mysterious, right? And so for me, the way I got into this field was not only by scientific questions, but it's really by a community, right? So this is a picture when I was an undergrad in the University of Mainz. So this was my old advisor. Where am I? Let's see. It's hard for me to see from this angle. Yeah, I'm here, right. So this is me, no beard, still long hair, right? And this was so cool because you can see it's a huge group, right? But even as a student, I got exposed to these new ideas. By the way, I didn't learn about these ideas in my classes. I learned about them because I did research early on, right? That's another thing I think that's very important. And so then basically, as I did more research and got more and more interested, my advisor was like, yeah, I want you to go to the US and learn more about these things. And I was like, okay, sure, I'll do this. So this was my first time in the US. There's my advisor here. I'm somewhere in the back. There's actually people on this picture here that are now professors at Penn State. I don't know if Binghai is here. Anyways, so there's friendships that have developed over the last 15 years. And so it was at this conference that I got to know Shusheng Zhang, who is one of the founding fathers of this field. And then now he invited me to spend half a year at his lab and really learn about this, right? And now this group of people here, they have really become really, really good friends. So for example, Joseph here, he was a PhD student at the time. When I started my PhD at Princeton, he was a postdoc at Princeton. So naturally, we started working together, right? So I think the cool thing about this kind of interdisciplinary broad science is that you make very human connections, and that motivates us, right? This is really fun. You get to visit different countries, different people. You learn to think about a problem from so many angles, right? So for me, this is always what I tell students. This is the cool thing about science, and I think quantum mechanics, quantum materials is the field to do interdisciplinary science. And with that, whoops. I thank you. Any questions, I'm welcome to answer.
Okay. First of all, I'd like to thank Dr. Meuchler for a riveting talk. Now we'll move into questions. So I'll just reiterate that at the beginning of the session, everybody should have gotten a note card and a pen. So if you have any questions that you'd like to ask, you can write them down, or maybe you already have. And some undergraduate volunteers are going to come through periodically on the aisles to grab them. And while they're doing that, I will just start off by posing a couple questions of my own. See where we can go. So just keep an eye out there.
You see.
talk so loud sometimes, I just think that everybody can hear me without a microphone, I guess. So the first question that I would ask is, you mentioned there's a lot of, talk and even mysticism sometimes about quantum mechanics. I can't understand it. Sorry about that. So, all right, we got it. So you talked about people saying that you can't really understand quantum mechanics, bringing mysticism into it. And so for people who aren't physicists or aren't even chemists who have a little bit of, interface with physics, how can people in biology or people in the community who don't have a sciences background get a practical understanding without, digging through textbooks?
Yeah, that's a very good question. I think the first one is places like these, right? I think universities are a conglomeration of knowledge, right? And so these should be the first place where people seek knowledge, right? The other thing, I think, that's partially what I mentioned, because this is such an interdisciplinary field, there's actually a lot of material out there that is free. There's a lot of talks out there on YouTube, or there's a lot of public science magazines. For example, Quanta magazine is a very, very good magazine that I like a lot. So there's, I think, an emergence of science writing that focuses more on the scientific problems, right? Which I personally like a lot. So I think for me it is seek contact with people who are the experts. There are a lot of resources out there already, but I think nothing beats like a real one-to-one questions.
Excellent. So I think we have our first question from the audience. So you mentioned that we do understand quantum mechanics. Can you explain what's going on when a quantum particle is observed and the wave properties go away and particle properties begin to dominate? Why the wave-particle duality disappears when an observation is made?
It's a good question. I think there's two questions in here. Why questions at a certain level are unanswerable. I'll make a point. Why does this thing drop? It's because of gravity. Why is gravity there? We don't know, right? That's the honest answer. So at a certain level, we always have to say we don't know, but it's not because it's mysterious, right? So in the same way, when there's this big example with the double slit experiment, you shoot a wave through a double slit, and you would expect that it interferes, and you measure it, and you see some interference pattern. And in quantum mechanics, it tells you if you measure through which slit it goes, you will never see this. The way I think about it, and this is not the most mathematical rigorous one, is macroscopically, if we measure the trajectory of a football, we're going to measure it with photons. Photons are so small that they will not affect the football going anywhere. So now, the equivalence of measuring, a wave-like particle going through something and then measuring it, it's measuring the trajectory of a football with a cannonball, okay? So what we're measuring with is actually of the same order of magnitude, the same order of energy, right? So I would expect that this has a much more prominent effect on the properties. This is the other way I think about it. There's nothing that tells you that the laws of nature at the microscopic level are the same than the laws of nature we experience at the length scale of a meter. What has to be consistent is that if we go from the small length scales to the large length scales, there is a crossover and that is well defined. We have that, right? People have made these experiments, at which level it becomes quantum and which is not. To me, these questions, why, are not always really well defined, because it's just a matter of fact that this is. Can we have a macroscopic way of thinking about it? Well, quantum mechanics doesn't allow for these notions, and I think that's just something we have to accept. It's the same way that at galactic energy scales, time becomes something like space. There's also no rational explanation why that is. I cannot explain this. It's just a matter of fact, right? We can do metaphysics and think about it, but I think it's always just a better way to think about it is this is how it is. What questions do we have to ask to prove that something is false? And people have tried very hard to say, this is ridiculous, this is nonsense. And every time they did, the laws of quantum mechanics actually, predicted exactly what's supposed to happen. So the way I think about it, it might be mysterious from our perspective, but to me, mysterious means we cannot control it, and it's something it's some sort of fate kind of thing. No, we can control it very well. And it forms the basic of many, many, materials and effects that we're using day to day. So that's how I think about it.
Thank you. Looks like a couple more here. So does it matter which direction the spin of the particles are in semiconductors, or just that they are grouped together?
Yeah, that's a good question. So it depends on what it matters for, right? If you just want to have a semiconductor you can make a transistor out of, it doesn't matter. As a matter of fact, in silicon and so on, the spins of the electrons, they basically always come together as pairs. There can be cases where they don't come together as pairs, but they're a little bit more separated. But if you're just interested in, the current as a function of voltage, as in a transistor, this doesn't matter. So now if you're interested in, can we measure the current of only spins with up as a function of voltage, then it matters very much. And then the materials we need to look at are very different from just normal silicon, right? And so this is one of the challenges that when designing new materials, you have to take into account.
All right, another transistor question here. Can you explain how exactly topological insulators would be used for digital storage or for other computation?
Yeah, very good point. So there's two things. The first thing is this property that these currents seemingly do not care about any defects, right? They go around them, whatever, they're not scattered. They only move in one direction. So that gives us innate resistance for properties, right? If the manufacturing is not perfect, there's a crack in the wafer, these materials, at least in principle, will not care. How it is in reality, when you actually make this thing, well, let's wait 20 more years. But at least that's why people got so interested in, is there's a tolerance to defects and perturbations, as one would say. How is this used? Well, there's, for example, people like Stuart Parking at the Max Planck Institute in Dresden. What he has the idea that you can build a so-called racetrack memory, where basically you have little tracks of material in which you can push magnetic domains. So a domain in which the electrons all go up, and then a domain where the electrons all go down. In order to push it, you need a current that's only consists of majority electrons of one spin. Topological insulators could, in principle, give us such a spin current, and that's why people are excited about this. There's a whole field about it, it's called spintronics. It can, of course, get very complicated, and one thing that I wanted to communicate is it's a big challenge to go from an idea to an actual device. We are in the place, I would say, where we have established a lot of ideas and we have shown a lot of proofs that these ideas work, but I would argue we're still quite a bit away from making real breakthroughs in terms of devices. That will just take more time.
All right, so more will spin. People really like spin.
You like spin? Yes.
So for the CERN-Gerlach experiment, why did the field have to be non-uniform? Sorry, why did the field have to be non-uniform?
Did it say non-uniform? Actually, I don't know. I think it's supposed to be uniform. I think what the important thing is that there's basically a field that goes from the north to the south, right? From the south to the north. That's how I think about it, right? So basically, as you go through here, you're experiencing the field more and more, and then basically the electrons with up go up and the electrons with down go down. I might actually be wrong. I have not thought about this in much detail, so I apologize. But that's how I, as a theorist, think about it. I'm sure there's an experimentalist who will whack my head afterwards. But all you need is essentially that you have a strong magnetic field in an area so the electrons can experience this long enough.
All right, so now moving outside of that, aside from electron spin, what are some of the other large questions that are current in quantum research? Yeah,
very good question. So I didn't talk about one really, really big field because I think June is going to talk about it in 1 or 2 weeks. So what people discovered is, I had this picture of these birds moving in flocks and so on, right? So in quantum mechanics, to show this, you need strong interactions between electrons, right? So electrons are charged particles and they can interact strongly. So it turns out that a new platform to study these phenomena, these collective behavior, is when you take a two-dimensional material and then you put another two-dimensional material on top of it and you slightly disalign them. This is called, the field of Moiré materials, because what happens is somehow, even though this twist is just very small, the electrons in these materials behave completely different than the electrons of a single layer. This was first discovered, I think, around 2018 or 2019, and it's really exploded, right? Because it was one of these things where people in the beginning had no idea why this really should be. And so now people are finding new ways to twist these materials. They have 3 layers and 4 layers, and how to control the properties of electrons, but just twisting 2 flakes of graphene, right? Which is, to me, when I first thought about it, I couldn't believe it. I thought this cannot be true, right? But it turns out it's very true, and it's a huge field. So I think June will probably talk more about this later on, but it's a huge new field, and very important.
Thanks for that. And now, so what are the primary challenges to connect the physics sort of model perspective to actual compounds in the solid state when correlations are very strong in quantum materials? For example, many body phases of matter, such as quantum spin liquids.
Yeah, very good. So we need to unpack a little bit. Okay, so there is one class of materials that these strongly interacting phases of matter, these quantum spin liquids. Essentially, these materials are where we have a lot of electrons, but the interactions between these electrons are so strong that we can no longer describe the electrons as basically behaving individually. So this is basically the ultimate swarm picture, right? So looking at a single electron just has no more meaning. We kind of need to look at what all electrons are doing at each time. So there's a huge class of materials called spin liquids. These are usually magnetic materials, which were explored. What is the challenge? So we can make a lot of models of these materials, but even doing the models is very hard, because if many electrons interact, you can show that on a classical computer, maybe we can store, if you do the calculations with the quantum mechanical equations, we can maybe solve the equations on a computer for 20 to 30 particles. That's about it. You can show that if you would just like to store the data that comes out of these equations, we would not have enough hard drives in the world to store this. This has to do with what we call some exponential scaling. So the more electrons you do together, the more you have to keep track of. This is not just linear or quadratic in the number of electrons, it's exponential. So, we do this routinely in our lab, so maybe we go to like 8 electrons on 8 atoms. We can easily do this on a small laptop. If we go to 20, we already need to go to a supercomputer, and our algorithms need to be very sophisticated. So one problem with these phases is that we can write down the equations and sometimes solve them, but in order to solve them, we have to use extremely abstract models. These models usually don't have atoms in them. They are just extremely mathematical. So the challenge is, how do we go from this mathematics to real models? And even if we had a real model, how do we even solve it on a computer? Quantum computers potentially could help us solve this, but that's also another 20, 30, 40 years down the road, right? So there's a huge research effort to understand how to better even theoretically understand these phases of matter. So now we don't really understand 100% what's going on theoretically. How do we even find them then experimentally, right? Because it turns out the hallmarks of such materials is that they do nothing. So maybe you know that you have a magnet, right? At low temperatures, the magnet is magnetic. At high temperatures, become non-magnetic. Well, these spin liquids and so on, one of the core properties is that they do not order, they do not become magnetic even to lowest temperatures. So it's kind of a null measurement. You have to exclude everything else to show that this is one of the states you're looking at. Turns out there are many other more trivial phenomena that can actually have the same result. And so this is a big question in the field. How can we design measurements and experiments that will prove to us that this is the desired ground state? It's actually very difficult, but very interesting.
Thank you for all those. And now from Zoom, we have a different type of question, which is, how do you tackle the ethical dimensions of quantum research? And can you share examples of where ethics considerations come into that research?
It's a good question. I'm going to have to be honest. I haven't really thought about ethics, so I'm not constructing any bombs, or I'm not doing, experiments on animals or something like this. I think the ethics, the way I can answer this question really is the only way is a little bit related to the distribution of knowledge. I think knowledge should be open and accessible for everybody, and that's very important. And so I think what we're trying to do is to communicate and make accessible all results to everybody. As I said, we don't really have ethics in the sense of, should we do this? Will this lead to a device that will kill us all? I would argue we're pretty far away from this, hopefully. But I think the ethical questions is more how do we communicate and how do we make research accessible.
All right, thank you so much.
Thank you. Thank you for coming.
Can you hear me? Oh yes, this is on. Thank you again, everyone, for coming today. Just please stay with us a few more minutes. And Lukas, please stay here for a minute. My name is Aleksandra Slavkovic. I'm a professor of statistics and associate dean for research in the Eberly College of Science. Lukas, on behalf of everyone here, online, and our college, I would like to thank you for this very educational and inspiring presentation on quantum mechanics and quantum materials, and especially for, I think, trying to inspire the next generation of interdisciplinary scientists. And I already heard one all the way in the back, so I don't know if you did. And we are truly fortunate in this college, in this university, to have visionary faculty as yourself, leading the next generation of disciplinary and interdisciplinary discoveries in quantum science. Thank you again. This is a little token of thank you from all of us. Okay? I would also like to thank Ken for his opening remarks and opening today's second lecture in this year's Ashtekar Frontiers of Science lecture series focused on quantum science, and for highlighting that Penn State truly is in a great position to lead the next challenges in quantum science with faculty in our college and faculty across the university. I must thank our terrific staff from the Eberly College of Science Communications Office and the Associate Dean for Research Office for organizing this lecture series. Today here we have Allison and Michelle for making sure the show is running. We couldn't do any of this today either without help from our undergraduate and graduate students. Thank you to KDN, graduate student in biology and science achievement graduate fellow, for moderating Q&A, along with Christopher Daggart, our graduate student in chemistry. We also have our undergraduate students who are members of the college's Science Lion Pride group. Hopefully I will remember the names, Tabitha, Penelope, Bella, and Claire. Wave, so I know, yes. Thank you so much again for helping and assisting today. To all of you, please use the QR code to provide us with some feedback. It's a very brief survey on today's lecture. As you heard me say this before, we use this information to plan the next lectures and to better engage with all of you. Please also leave your email address so that we can be in touch about the future talks. If you would like to learn more about the next 4 talks in this lecture series, please go to science.psu.edu/frontiers. You can learn about the upcoming talks, and you can also start viewing some of the recordings from the previous years, and I think soon enough we'll have recordings from this season as well. Again, thank you all very much for joining us on this Saturday. We hope to see you next Saturday, and have a great weekend. Thank you very much.